everybody? Can you hear me at all, Andy? Am I on off mute? Hopefully so. If you do, I'm going to just go through. There's a QR code. If you could all scan that during the presentation, the bottom left-hand corner is the QR code on every single slide. There'll be a couple of questions a bit later on in the presentation that that the questions will pop up on. So just be patient, and hopefully the technology will work. Fingers crossed. So thanks for the introduction, Andy. Let me just see. So I'm going to go through today Miller Mainline, the projects, the numbers, OLE static assurance, the legal position via NTSNs, what that means in test train requirements, conclusions, and hopefully lots of time for questions and answers. And as I said, please scan the QR code. It should work. And in the bottom left-hand corner is a QR code on every single slide, so you can get it repeatedly throughout today's presentations. So a quick summary of Midland Main Line. It's about 77 single track kilometres. It's a 24-mile scheme length. We've introduced 5 substations. One of those substations was a feeder connection, a 400 kV to 25 kV step down. We've changed 25 signal heads. We've had 7 track interventions, 11 voltage control clearances, and we've applied a form of 12 bridge interventions via what we call VCC measures. The Kettering to Wigston on the Midland Main Line is this little bit here. That's the bit that we've just recently commissioned, and that's the bit we're going to be speaking about today. So a bit of reflection on what I define as my assurance pyramid. We've got 77 single track kilometres. We discussed that already. We've had over 210,000 site checks. Of those site checks, we've got about 10,000 physical quality check sheets. They're check sheets that we go out on site and actually physically undertake. So PAL, for example, will develop a check sheet. We've had about 1,800 site referrals and field change requests. That's stuff that's happened on site and or where we needed to change the design. We've had about 1,233 snags and defects as part of our AMP process. So AMP process is how we hand the asset over to the maintainer. We actually did physical checks on site, and we had 168 machine shifts just checking what we've already built. So we've done site assurance, we've done quality check sheets, we've referrals, we've done AMP 16s. And that was all underpinned by 163 Form Es, of which 422 were needed for 4 energisations. So that's even before we did any form of train testing. This is what I define as business as usual. On top of that, we're going to discuss some of the options today. I had 26 shifts of train testing in order to support the legal requirement under the NTSN. So a hell of a lot of assurance went in before we even ran a test train. And I'm just going to touch on some of the reasons on the why. Sorry, somebody's calling me. Not very well timed. We learned from previous experiences. So I was the CEM, the Contracted Engineering Manager for London to Corby. We knew where to look. So as part of our static geometry checks under a Form E, as we call it, we put a lot of extra effort into droppers in terms of the position in the long track, tangential wiring overlaps, inline neutral sections, section insulators, bridge arms, cross contact bars, and particularly Z droppers. We enhanced we knew that when we ran a test train, we would get areas of tension or areas where it could be quite problematic. These couple of pictures that I grabbed from my old role. On the left-hand side, we're going to go into this a bit later, is an output from a test train showing sort of 2 higher peak forces identified in blue here. And this is actually a Z dropper, now being mitigated and removed as part of UK Master Series. But what does this actually mean? Does this transpose to an actual thing on site? I didn't know, but I did speak to the route, a guy called Paul Herring, and did send me some evidence of some highly worn contact wire over about a year's surface at this very specific location. So what the test train sees in these little dots here when it's running through actually transpires to be an actual physical asset that's deteriorating that could cause a long-term issue. So we knew where to look, and we put more assurance around that before we ran a test train this time. So what do we mean by OLE static assurance checks? A picture of a typical height and stagger gauge where we go out and take a physical measurement of the contact wire, generally at the registration point of each OLE structure. For these, we're all used to entry into service, so the height and stagger sheets and quality assurance is all underpinned by a very sort of prescriptive set of requirements within Network Rail's standards. So, for example, the extract on the right-hand side is a height and stagger sheet. So we go out at every single location, take a height and stagger, we do an assessment on gradients, maybe deviation, and say it's okay, it's compliant. But what we did, we asked, was that enough? What can we do to further de-risk the requirements of train testing, or further de-risk the requirements of having a rip down when we are physically train testing? So we didn't have the opportunity to use the NMT train, so we couldn't scan the overhead line. So some of the technology we used on London's Corby, we used, I think, Paul Dobson's by OCR's Wizard that took height and stagger measurements at a very regular interval to pull out an output from the contact wire. So we went out to the market and we found a product called a mobile mapping device, which is the device on the right-hand side, this little thing at the top. It's agnostic, so it can fit on any type of machine. We didn't have the NMT. We needed to quickly scan the infrastructure, but we needed to extract the contact wire as quickly as possible to then proper look at the health of the contact wire position versus the traditional approach of just doing height staggers at every single structure. This is an example of the mobile mapping output. It's in point cloud. We've got a few add-in AI tools, and this is the AI tool identifying the contact wire and extracting the contact wire into a sort of manageable output, i.e. we got the point cloud, that's great, gives me lots of data, but we needed an output of that. So you can see there, it's picked up the contact catenary automatically, and now we can extract that into something useful. This is the useful part. You can output this into Excel. The yellow curve here is actually the position of the contact wire over retention length, and this can be extracted in a matter of minutes. So the AI tool finds the contact catenary wire here, so therefore it knows how high the contact wire is, and also the stagger. And you can see here that we go from a nominal wire height and we start going down slowly into a bridge and then back up again when we've got an overlap. The green curve here is the contact wire. So again, the stagger. So it's actually extracting the position and the stagger. So it does vertical and horizontal checks. Towards the right-hand side of the screen here is an extract of a span. And you can see where these little dots are indicate where the somebody's not on mute. Indicate here where the droppers are actually are along track. So we're not, generally speaking, we take the contact wire position at the blue lines here, which is a structure location. But with this type of technology, you can actually have a look at the as-built profile of the contact wire, which is vital to understand the relationship between the pantograph and the contact wire. So what do we do with this? We use a company called T-Riz, and we had the as-built position, but we needed to overlay that against the design position, but the physical design position of the contact wire at that location. The extract here, again, this is a different wire run. It's heading down towards a bridge. The contact wire is slowly reducing from 4.8 meters all the way down to 4.1. The brown line here is the indication of the as-built position of the contact wire at high frequency. And the blue wire here is the design position. You can clearly see there's a sort of subtle deviation between the as-fitted contact wire profile and where it should have been. And we're able to pinpoint these areas, identify these areas before we even ran a test train or any form of entry into service requirements for the train operator, EMR, and or train testing. So we actually knew before we ran anything where to look for. So test train requirements. This is the train in the background that we built in the end. We're going to just go through some of that now. So under the NTSN, there's two specific clauses that are applicable to train testing. 6141, which is simplified, is to validate new OLE systems. So London to Corby, the previous overhead line system of Miller Main Line I worked on, we were remitted to do what I call IC testing, which is to validate the new system against the design parameters. Miller Main Line Kettering to Wigston section that we're talking about today was principally about 6245, which is construction assurance, which is geometry checks only. Simply anything above 75 miles an hour, you've got to run a test train. So yes, it is a legal requirement. The industry didn't have anything available to support our needs. There were a lot of specific needs within the NTSM, which can be read sometimes as quite a binary set of requirements that we had to achieve. Sectional line speed, so we had to achieve 110 up to 125 miles an hour. We couldn't reach out to the train operator who have and are introducing their new Class 810s onto the network, but we couldn't align our programs to suit, so we had to build something ourselves. It took me from a blank bit of paper and a lot of help from the supply chain we'll discuss shortly, about 18 months to plan. And that ended up being about a 2-month train test program to deliver the requirements under 6245. So who's who? What makes up all the constituent parts of a test train? Sort of treated this like a system, and it's not just overhead line, it's not just rolling stock. It's just not just a depot, nor is it not just a set of requirements. We needed an electric EMU to support the requirements. We use Eurofenix to do that. We then used our sister company, Colas, to provide their Class 43s and Mark III coaches. We then needed a pantograph to fit the Class 91. It had to be an interoperable pantograph. Again, we'll go into that shortly. That was originally procured through Wabtec, and then we ended up getting the pantographs through Eurofenix. Importantly, we then used Serco to instrument the pantograph. So we needed to instrument a pantograph and had in order to get the results to support the authorization. We then used another sister company to do the engineering change. So any changes to rolling stock, inclusive of the pantograph, had to go through engineering change, and that was then supported via the safety case to allow the physical train to run on the infrastructure. All that was wrapped up, and we had to store the train. We had to gain access to the train. We had to gain access to the roof of the train. So we used UKRL, Leicester, and that's where the train was stored, maintained, and moved in and out from. Then there's me and my entry into service team in terms of how we provided the assurance to allow the test train to run, and we were the system integrator of all these different constituent parts. We then had to squeeze the train physically into the network via route planning, squeezing between the trains, or have dedicated access opportunities to run our train. We then used a company called TRIS, who took the data from Serco and were instrumental in identifying the pre-construction assurance and hazard assurance, but also the output to the technical file to NCB and the ORR to say whether or not we were compliant or not. That was all wrapped by Colas, who brought it all together. We ran the train under their safety case. Note Rail, bit of a light touch, but they are the project and my client. And we've also got two important constituent parts here, NCB and also the RRR. So there's a lot of stakeholders, a lot of moving parts on a very, very sort of complex, not off-the-shelf problem. So the pantograph, just checking time. Yeah. We needed a pantograph. The Class 91 is a mid-80s electric vehicle that had what they call a HSA pantograph. The NTSN talks about the pantograph having to be an interoperable TSI pan. So we chose a HSX in discussions with both Eurofenix, Colas, and importantly Serco. it achieved the line speeds that we wanted. We wanted to run the train at 125 miles an hour, and the HSX could achieve that. It has got good historic performance, but HSXs are actually designed for IEP Class 800X trains. So the Hitachi trains, particularly those on Great Western and those that have been introduced on Midland Main Line, generally will have a HSX pan. And if you do want to order a pan, they are on a very, very long lead time. We started going down the path in using a Class 90, and we procured a HSX hybrid pantograph for Class 90 train in 2023. However, the Class 90s were discontinued, so we had to look at alternatives. The Class 91 was chosen, but the Class 90 pantograph that we ordered wouldn't actually fit a Class 91, so we had to make some last-minute changes to make sure that the HSX that we were actually ordering would actually fit the very unit that we've procured. A bit of chicken and egg. So the rolling stock, the Class 91 did have an existing HSA and was removed and replaced with a HSX hybrid. We then had to create what we call a VMI, which is a vehicle maintenance instruction. And that, so if we take something off, we're going to stick something back on. But the thing we've got to put back on, we've got to make sure that everybody is aware how it operates, how to maintain it, and how to replace it in event of an issue. We made some significant modifications to the 91. A lot of them were permanent connections in terms of through cabling to allow the Class 43s at either end to talk to the 91 and vice versa. And also had to make some modifications to the HSX to support all the measuring equipment that Circa were using to actually provide instrumentation for the pantograph. Class 91 modifications. Interestingly, I don't know if you can see just here that there's a K off that's been removed. That should say keep off. So the pantographs that we actually ended up getting were amended in their previous life to actually fit a Class 91. So we had to make some adjustments and had to move. Oh, excuse me. We had to make some adjustments to the actual physical top of the rolling stock in order to make sure the pantograph would fit. So we're trying to squeeze something that shouldn't be there onto something that we needed to use. Yeah, that's it. So train testing requirements. We needed to achieve 125, which is maximum speed on the UK network. The train operator EMR are looking at introducing Class 810s. And they are bi-mode trains using both diesel and 25 kV electric. What we ended up doing is the pantograph, we'll go into this shortly, had to be raised and lowered at line speed. Electra, which is the name of the train that we used, in terms of what the two units, the Class 43s, had about 4,500 horsepower. However, if we used Electra, as in the Class 2 Class 43s and the 91 together, it's about 10,000. So we had a significant amount of more horsepower if we had all three engines all running at the same time. And these were definitely considerations when we were operating the train, running the train, and particularly around areas where we had to achieve high acceleration. So this is a very, very light schematic of the scheme. You've got London on the left-hand side, or Kettering on the left-hand side, end of wire here, and Leicester Station just towards the right-hand side of the end of the wire. EMR, through the project, have determined two locations, or bi-mode locations, when the train's running from left to right. The future Class 810 pantograph down areas were indicated just before the end of the wire, obviously, and on the way to London, the bi-mode location again was determined as a location about 3 or 4 miles away from the end of the wire. A big discussion point was actually why have a Class 43s? Why couldn't we just use Electra in electric mode? We had a significant amount of issues over track access, and it took, from a standing start, approximately 6 or 7 miles using the Class 43s to go from 0 miles an hour to 125 miles an hour. We couldn't do that. We couldn't rely on, just show that. And in the opposite direction, We also had the class 43, would take about 2 miles to go from 0 miles an hour, from 125 miles an hour to 0 miles an hour. What we couldn't have is that then starts to restrict the amount of overhead line that we test at sectional line speed. So we had a risk that we had to achieve as much we had to achieve the largest speed possible in the amount of wire that we had available, and slowing the train down and speeding the train up from a standing start just wasn't viable. Importantly, we would never have got the access. We go into this shortly, that the possession, we didn't have possessions. This wasn't a dedicated route. We were squeezing the test train runs between services, so we just didn't have the available track access to undertake this methodology. So the track access and availability of the route was absolutely geared to develop the decision around panning up and panning down at higher line speed. So we developed areas that we temporary areas, or PCO signs, either pan up boards and pan down boards, specifically for our test train. We signal sighted these, and we were able to develop a system where we could, somebody's not on mute.
And go into the detail. There's that. Unfortunately, all of them.
Is that done? Yeah. Thank you.
Simon, you've gone on mute now. You're still on mute, Simon.
Is that better?
We can hear you now, so no.
Yes, yeah, we can hear
you.
Yeah.
Right, typically, when I go through it all, sorry. I think I was put on mute by accident. Maybe that's a good thing.
Now showing us presenter mode, which may not be what you intended.
No. How's that? Is that better?
Yes, it is, Simon.
Yep.
So I forgot where I was. Apologies. Yeah, so we developed a strategy where we would, in order to fit our train service between existing services, we had to develop pan up and pan down temporary boards to inform our train driver at speed where to raise the pantograph and also lower the pantograph. So going from south to north, we would position a board that was signal sighted, as you can see here on the left hand side. This is an example of our signal sighting forms that would allow the train at speed to run past the board, and as it went past the board, it would lower the pantograph at speed, and in the opposite direction, it would go from north to south, it would do the same. So these were strategically placed boards. Interestingly, what we had to do, we had to make sure that going northbound, that the boards were positioned beyond the point where the EMR needed their signage. So what that meant was, when we were going through authorization, we had to always test more than the train operator would use, and that was a sort of sub requirement that wasn't necessarily identified clearly in the remit, but we developed that remit hand in glove with EMR, and we got where we needed to get to. So the number of test runs, quite a lot of verification and validation were needed to develop a sort of system approach from a train testing point of view. We had to do 2 lots of train testing, vane angle adjustments and what we call tether testing. The vane angles are in the middle. These are the aerofoils, as they're commonly known. These we had to make sure that the angles of those were adjusted in order to keep the pantograph performance in both directions the same in terms of physical uplift. And then we had to do the tether testing. Those who don't know, the tether testing here is there's a picture here, and you've got literally tethers that are forcing the pantograph down both are needed in order to fulfil the requirements of the equation that allows for the full NTSN run. There's some additional pictures here on the right-hand side that UKRL helped us to support on when we needed physical access to the pantograph at each end of the wire run. So we had to get on top of the unit, we had to inspect the pantograph for maintenance, but we also had to change batteries and do some stuff around making sure the instrumentation wasn't damaged after each of the wire runs. So just going through from top to bottom, we had 6 runs to validate the vane angle adjustments, which is pantograph, the knuckle trailing and the knuckle facing. We then had to do the tether testing. The requirements of 50137 talk about, I think it's 25 mile or 25 mile increments of line speed. So we had to both test it at 50, 75, 90, 100, 110, 125 miles an hour. Quite difficult to do because the tether testing needs to be tethered below the contact wire, and you generally have about 50 to 100 mil clearance between the contact wire itself and the physical pantograph. And this started to also steer why we had to diesel haul the unit, and you couldn't have an electric haul because obviously the pantograph's not touching the contact wire. We then sort of started, we then did sort of what we call pre-NTS construction assurance test. This is a health check, progressive line speeds at 30, 60, 85 and 110. Simply, I just call this warming the wire up. This is about the pantograph touching the contact wire, seeing what we've got before we run the true testing. The NTSN testing, that's an obvious requirement. That's the data from that supports the technical file that will go through to authorization under the ORR. And there's also some other testing that's also needed, such as uplift testing. We'll go into that bit shortly. VLVT testing, that was an interesting one, and we covered that within this. That's nominated. These I won't go into this too much. I think we'll have access to the presentation. These are some of the planning sheets that we used to develop the scope. These planning sheets were developed with Serco, with Colas, and then Colas would go away and actually then try and plan a train path to satisfy what the requirements would be, and those requirements were defined by the project in keeping with the sort of the NTSN set of requirements. So you can see, hopefully the videos work. This is the train in 2 different areas that we built. At the bottom here, you've got a Class 43, you've got 2 Mark III carriages, then this Class 91 from Europhoenix that we adapted with an HSX hybrid pantograph, 2 Mark III coaches and a Class 43. We needed all the coaches, 2 of them particularly extra, from 2 to 4 to achieve additional brake force needed for 125 mile running. So this is the output. So we did all that work, and Serco did a great job in instrumenting the pantographs, and this is an output of their live pull. This is going 60 miles an hour at the top here, and this is the force in newtons. And hopefully we'll have a look at the next one shortly. You can see that the pantograph force going 50 miles an hour is quite static. It's sort of roughly around the 90 to 100 newtons. But every now and again, such as this point here, you get a bit of a peak. The good thing about slow running is actually you see an exaggerated force. So you can actually pick out a lot easier where we might have a problem versus potentially, if I click here, going from 110 miles an hour to 125 miles an hour, the frequency is greater because obviously you're going faster, but you do see some higher peak forces that are unknown because it's just an output. So we've got to try and find where those forces are. But this is a reasonable output in terms of what the overhead line system would look like, particularly at the higher speeds. I think actually this here is where we tested the 95 metre span. And I think Serco can identify issues as we go, and we can pick those up and try and find where we might have high exceedances later on. Another requirement is uplift testing. So the NTSN is sort of a bit circular, it's a bit of a circular reference sometimes, but it calls that we need to do uplift testing. So we position the camera at sectional line speed. So this is at 110 miles an hour. And we take a picture of the pantograph going past, and the output on the right-hand side is the static position here. And then as the pantograph passes, you can see that the registration arm is physically uplifted, and we take that measurement. And that's done via T-Riz did this for us. The drawing here on the left, or the graph here on the right, is if a train is going from left to right, the pantograph's coming along, and the biggest spike in terms of displacement is where the pantograph is underneath the contact wire, and then you get a rolling reduction of frequency when the pantograph's moving away from the contact wire. So this is 110 miles an hour, but we actually found that the predicted uplift is very, very, very similar now to some of the stuff in simulation, very similar to what we're seeing on site, which is great. So conclusion, there's a few of these. So we showed a slide earlier on our static assessment, and it's by no accident I've repeated this slide. So we saw that the contact wire is a little bit below where it should be there and a little bit above. This is really zoomed in high. We now overlay that with the actual test train results. I think this is at 110, maybe, or 100 to 110 miles an hour. The frequency is generally quite consistent, but we do get these discrete low and high peak forces. So that's indicating the direct correlation between deviation from the contact wire, design position, and actually what the test train is seeing. So it goes back to one of the slides at the very beginning, which is we know where to assess our health, our overhead line health. We know where to look for, and we're getting direct correlation on the output of the test train where things aren't quite right. So whilst these aren't quite right, it's still compliant, but it could still be a little bit better. I've got another example here where we overlay the contact wire slightly slower. I'm not too sure how fast this was going, but it's a slightly slower line speed because the frequencies are a lot more drawn out. It's not as exaggerated. But you can clearly see we've got a high peak force here. It's pretty obvious. And what we're able to do is directly correlate to that on the static analysis that we do prior to this. So once we find an issue, it's a needle in a haystack, but the technology that we've got now, we're able to identify where that issue is, what the issue is, and actually resolve it before it's a problem. So what does this actually mean? So the report that we put together to support APIS said from T-Riz to NCB, we don't exceed any of the deviations. The uplift forces are okay, and we didn't see any form of unexpected issues with the system in terms of construction assurance. Interestingly, we just received the car from NCB. It's now been submitted to NRAP, and I believe we've got confirmation from NRAP, and we're now going to submit to the RRR. And it's basically saying that the evidence provided and the methodology that we've done achieves is compliant. So we now a brilliant sort of project and national win, but we've actually got a compliant output from both the project and also from NCB as well. Just going to ask people just to scan it because we've got the questions coming up next, which is quite well timed. So I'll give a couple of minutes. I'm hoping this will work. Yeah. So over to you guys. In terms of the amount of effort, I've squeezed this into 40 minutes. It's quite a lot of my life in 40 minutes. How much do you think train testing costs this project? If you could just have a look at the options on the screen on your phones, iPads, and feed that back, that'd be great. We can have a look at the output shortly. Brilliant. So still going. Great. I'm asking Andy now if you could just take a snip screen of that output, or somebody in my team perhaps could take an output and send that on to me. That'd be really useful, and I could put this into the PowerPoint afterwards.
Sarah, could you do that possibly, please? There's a
Brilliant,
thumbs
thank you
up
very
then, so I
much.
hope that's done.
Oh, that's great. Okay, thank you very much. We'll give the true answers shortly. And importantly, for NTSN compliance, how many OLE adjustments were recommended after our train testing? So, given all the work we did on static analysis, enhanced assurance, we knew where to look for all that good stuff. When we ran a test train, did we have to go back afterwards and actually do any adjustments? Yes or no? How many adjustments do you think we were needed? I'll leave this a little bit because I don't want people to look at the percentages and just follow suit like lemmings. Okay. 1 to 10. And 22 people. Yeah. Interesting. Thank you. So, how much did train testing cost this project? So, for the next phase, Neverrail have put in a provisional sum on actualised costs to support further route sections that have been currently going out to market for tender. So, the actual true cost was around about £3.3 million. That included pantograph. We had to buy pantographs. We had to build the train from scratch. We had to start again. We had a clean bit of paper. I think that's high, too high for the output. But I think going forward, future route sections and future schemes should be able to reduce those costs significantly because we've done a lot of the hard work for the industry. And for NTS, how many adjustments were recommended after train testing? 0. We didn't do one adjustment on site that was needed to support a non-compliant NTSN issue. So this is where we are now. In terms of compliance, we issue a Form E under the entry into service set requirements for the project. It takes 8 weeks to test. It takes a further 4 weeks to write a report to say the results are good or not. It takes about 8 weeks for NCB or another authoriser to say, yep, we're happy with what we've got. And sometimes there's a back forward. So that whole entire process is about 5 months. So from a Form E, so once we've physically finished construction, it takes 5 additional months to support a positive to say that it's good, it's safe as per the NTSN requirements, and then we can start moving into the direction of getting authorisation by the RRR. Where I think we should get to is perhaps we know where to look. So should we do some enhanced construction assurance only? We need to underpin some of that output within a Form E, or perhaps a form of enhanced requirement under a Form E. Skip out test training completely and just go straight for APIS. So I think the evidence that we've shown and the methodology that we've applied proves really that as long as it's installed right, we shouldn't have to continuously test a system that's been tested multiple times. So it's all about the construction assurance and not necessarily applying a binary clause that will achieve that doesn't achieve any sort of valid or operational or safety output in my view. And that's it.
Simon, thank you very much indeed. A very interesting presentation, and also a very good set of questions that you raised at the end. My screen's suddenly... there we are, back again now. So questions that were asked. I think I'm going to go to the last question first, which is from Luke Marsland. And this follows on very closely from what you've said. That given that you installed an approved OLE design range UKMS, which has been assessed as IC and has an existing ISV, accompanied by a strong construction assurance regime, which, as you say, is now business as usual for projects. What are the next steps to refresh the actual NTSN to remove this dynamic assurance requirement?
That's a good question. Thanks, Luke. So about a year ago, about 12, 14 months ago, the RSSB were asked via the DFT to challenge maybe some of the NTSN or TSR requirements from Europe. So the TSI is a European legislative backbone, and we've got our NTSN, which is the equivalent, which is a post-Brexit. I think the DFT were right to challenge that, you know, we should be doing what's right for Britain, and therefore, if we think there's over-onerous requirements in the NTSN, we should challenge those, and that's what we are currently doing. I believe the technical authority through the RSSB, including the Energy Standards Committee, started to look at some of this stuff. And one of the points of doing some of the stuff that we've done on Middle and Mainline is to start build a story of compliance and evidence rather than hearsay. So what we've done, and we've helped put together reports, and we've done an evidence-based approach to actually try to tell a story of why it shouldn't be needed, rather than what I think is my opinion. So hopefully that answers your question, Luke. But it'd be interesting to see if others can actually follow suit and start stacking this up, so we can have more evidence that we don't actually need to do something.
Yeah, that's great. Thanks, Simon. Yeah, it was mainly just raising it because obviously, you know, you're kind of like over the 3 million mark for your cost, but TRU is experiencing kind of E1 project alone sort of close to 1 million, and we've got 4 more of these stages across the TRU program. So I guess supporting what you're saying, is this the right thing to be doing as an industry?
Yeah, it's a good one, Luke. There's obviously the cash. There's also program, but program is cost. So potentially, if you're dragging out a program for 5 months at a £2 million per month burn rate for prelims to sit there waiting for stuff, the physical cost is one thing, about £1 million, but then you are putting a lot of attention on programs that are linked to sort of DFT milestones. So if you reduce that and negate that or eliminate that requirement, then all of a sudden you're making some significant savings in my view. So it's not just capital cost, but it's sort of system cost. If it's just not needed, then you could spend your time doing other stuff or start working on the next route section perhaps.
Yes, it was interesting for me to see the intersection bridge at Cardiff, where I believe the juice was actually switched on the Sunday and the trains were running electric underneath the bridge on the Monday, which was, the ultimate. And, given how that was pushing the envelope out, or pushing the envelope in, to be precise, with that bridge, I was amazed that electric running started immediately.
Yeah, it's an interesting, Andy, I think, and it goes back to the trigger point of the NTSN. It's above 75 miles an hour. So anything below 75 is under entry into service for me. It's just business as usual for us. My suggestion is either complete removal or certainly perhaps a reassessment of those line speeds, and maybe the evidence we got now should be pushing those line speeds up to 125 miles an hour. So we just don't have to do this going forward. Okay,
thank you. Simon Warren, you've got your hand up.
I was just going to correct you, Andy. The testing at South Wales was completed on New Year's Eve. The report was completed on the 3rd of January, authorisation on about the 4th, and trains running on the 5th.
All right, 5 days. My case still stands, even if my numbers were inaccurate.
Yeah, it was a lower line speed at that point.
Yeah, thank you. Alan Darby, you wanted to say something still?
No, I was going to say the same thing that Simon he just said. Obviously, I was there as well, so just to correct you.
Okay, thank you. Mick Bloor.
Oh, Simon.
Hello,
is the train nobody, mate. Is the train still available?
So parts of the train is still available, Mick. Yeah, so it's a good question. So it's not available as it is. It costs a lot to put a train together. It's generally a weekly rate or a monthly rate, so you can't have it hanging around. The modifications that we did, particularly to the Class 91, were permanent, and Europhoenix's managing director was happy that the modifications to the 91 wouldn't sort of affect the operation of the Class 91. So Luke on TRU asked a question earlier. They're hopefully going to use Electra, the train concept, to support his work, Mick. So we've done a lot of the system engineering, the safety case. Serco have developed the engineering change to allow a HSX to go onto 91 and where to put all their load cells, etc., accelerometers. All that's all off the shelf now. So we've learned the hard way, Mick, but we're hoping that it's sort of now off the shelf, if that makes sense. So it's not a Network Rail IM thing. It's very much in the supply chain, but through COLAS, this train is available.
So it shouldn't suffer the same fate as those Class 86s then.
We had a long discussion. Around using, I can't remember what it was, like Class 66s and the binary assessment of the NTSN. So this all sits in the NTSN. There's no sort of fruit or line standard that covers this off specifically, but this is geometry testing only. So we had to use Class 43s because we needed something that went 125 miles an hour.
Yeah, sure.
It was clear the NTSN talks about operational line speed. So if the sectional appendix says 110 and 125, it needs to go that speed. So things like Mentor, that I think had a restriction at the time of 90 or 100 miles an hour, could not be used because it didn't achieve the project remit. And that's all part of the problem. There's no, it's a binary allocation of a clause and not necessarily a sensible allocation of the clause. Does that make sense, Mick?
Oh yes, yeah, by all means, yeah. No, I know you try and get rid of the NTSN requirement, but the sheer basic engineering requirements would probably remain in some means or other. So going forward, and the capabilities there, which is good.
Okay, thank you. Right back at the beginning with your triangles, Simon, and Mark Smith was saying, is 1233 snags a lot, or is it not very many in terms of the whole scheme?
It's an interesting behaviour because snags are generally usually a negative thing. What we've ended up doing is we build it, and there's a lot of internal snagging. So we progressively build, and we progressively, if we've got an issue, we need to know about it. So those changes, those snags are identified and closed out. So we're quite open with that philosophy. So we're whilst the snags look high, we prefer to know the snags and clear the snags before we run a test train, then have snags post test train. So it's taken quite a long time, but behaviourally, if we feel that if there's an issue, it needs to be raised. Is it normal? Possibly, possibly not. It just works for us. So we prefer to know about them than not know about them and have issues in entry into service.
Thank you. Okay. Neil Dance asks, did you undertake any analysis of the faults and snags to look for root causes?
Yeah, we did. So the static analysis we did prior. So the mobile mapping stuff that you saw within the presentation, that generated a very detailed contact wire position. We then gave that to T-Riz, who've got some bespoke software that can actually plot the OLE design, and we mapped them across each other. And we wrote a report. And prior to the test train going out, we identified preferable or works that could be done prior to test train, niceties in essence. It's really difficult because you can't just say if a contact wire is interoperable or not. You just can't do that. It's you just don't know what it's going to see, but you can definitely mitigate, and that's what we did. We already knew where to look for because we tested 200 kilometres worth of wire runs, part of London to Corby entry into service. So at the start of the presentation where we said, overlap, Z droppers, etc., we knew where to look at. We put some enhanced assurance around those areas, and we targeted those areas rather than standard line of route areas. We also did some things like we did actual span lengths in terms of droppers. So every span was developed to 0.1 meters rather than to the nearest meter. So we had a sort of philosophy of if you drop something, the most critical interface is one I don't think we spend enough time on, which is the relationship between the contact wire and the pantograph. So, and dropper positioning, dropper lengths are a key part of that.
Thanks. Neil also asked, I think I know the answer, but I'll put the question anyway. Hang on, it's disappeared up the top now. Did you do any overspeed testing?
No, we didn't. So the complexities that Wigston to Ketton or Ketton to Wigston section is actually 110, but we actually tested the unit to 125. So we never actually needed to go 125, other than the fact that TRU and the rest of the industry needed perhaps a train consist to go 125. So we did do plane angle adjustments and testing to 125 and tether testing. What we didn't want to do is test to 110 and then leave it for somebody else to potentially do some testing from 110 to 125. We wanted to try and achieve something that was more off the shelf for the next project rather than potentially just leaving open gaps. So no, we didn't, but the train consist was able to go faster than we actually needed it for.
Okay, thanks. We're running tight on time. There's a very interesting question from Malcolm DeBell. Your assurance pyramid suggests a significant paperwork overhead. Equally, developing and improving the test train was an overhead the project had to bear. How much as a proportion of the overall budget did all this cost? And if the section of overhead line had been significantly longer, would the assurance overhead have been proportionately lower?
Oh, that's a good question, and that's an important one, particularly to reduce white collar staff, because that's where a lot of these electronic a lot of these costs are sunk into. I think the future should be a rowing back on QA, in my view. I think from Northwest electrification phase 1 and 2, and some of the tension around entry into service, and there needs to be, I think we've gone a little bit too far to the right. I think there needs to be a view on what's important. I think we need to learn where we are at the moment. I think we've got a little bit over onerous on QA, on nuts, bolts, washers. I think we should be putting more emphasis on competence of people. There's always a balance, but I think we need to think about what good looks like, but also what's important. And the contactless and enhanced assurance, we're doing some work currently on what that might look like. I think you could reduce numbers. I think we should rely on our people to actually, if they go out and build something, they should just build it. I don't think you need an army of people to sweep up and say things are built and things are talked. There's a balance there, and I think as an industry we are improving, but I think we need to improve quicker in order to get electrification back on the agenda. I don't know if that answers your question, but it's quite a complicated one.
Okay, thank you. There's a question from, and forgive my pronunciation if I get it wrong, Christaps Pastelions. Is the testing train only used for new installations, or is it being used, or could it be used, for network-wide quality runs associated with OLE in the same way as the track recording trains aid maintenance teams?
Yeah, it could be. We had some discussions with SPL looking at a piece of work south of Bedford at the moment when we do some retensioning. So we actually had some discussions around putting a test train on to support the testing of some of the existing overhead line wide ones on the London to Bedford section, which is a Mark 3B section. It's agnostic. It does, the pantograph doesn't know what it's looking at. So it doesn't matter if it's new electrification or existing electrification. The pantograph is it's an approved UK specific pantograph. So we could have done that, yes. The pantographs are currently sat at Sercos. They're owned by Network Rail now. So these things can be used and instrumented wherever the client or clients want them to be. So yes, it could be.
Okay. We're almost out of time now. So Simon, there's a lot of other questions in the chat. Will you be able to work your way through these and put answers on in the chat over the next few days, possibly, so that people can see the answers to their questions?
Yes, I can do that. However, PWI or yourself, Andy, want to do, I can either reply back to the chat if it's fully closed off, or another way. But I can do it on the chat.
Yeah, usually it stays open for some time afterwards. So if you could do that, that would help, because we certainly haven't got the time to go through anymore. Okay, well, Simon, thank you very much for the presentation. Thank everybody for the questions that have been asked, both those that we've been able to deal with and those that we haven't. It's been a splendid and very interesting presentation, and as an ex-Nottingham division man, obviously particularly interested in the routes, and look forward to seeing the wires diving under London Road Bridge in Leicester eventually, and going on further north. And as I say, the PWI LinkedIn page, there'll be a dedicated page to this, and the answers to the questions can come up there. Final thing then is that the next Listen and Learn session is on the 4th of February, listening for safety concerns and how CIRUS can help. Thank you all for coming, everybody. Splendid turnout. I think I saw 271 at peak, which is amazing. Simon, thank you again for a very interesting presentation, and I wish everybody a very good afternoon. Thank you.